I'm going to attempt to run this presentation from my phone because I wrote notes that I don't want to forget. We'll see how well this works. So how did this start it? In 2012, I set a record for running Linux on the lowest end machine at the time. It was an 8-bit AVR. It was kind of cool. It was the first time I was on Slashdot. Back then, I used the 16 megabyte SIM. This is what RAM sticks were before they were big. And an AppMega microcontroller, and I emulated an ARM chip on it. It was pretty cool, and I was curious how this record would stand and how long. And this is what it looked like. Not very professional. This is before I learned how to design PCBs. I still don't know how to do it, but now I pretend that I do. And occasionally JLC will make things that actually work. So this record stood for 11 years. And I was beginning to think nobody would actually beat it. But then in 2023, there were a couple of things that happened. So first, there was this gem. So this was somebody using a RISC-V emulator on a slightly smaller AVR. And I knew this was actually targeted at me because the README called me out by name, saying that this is actually lower end than mine. So yes, this was a guy called Gyang Ving Hoc. I hope I got that name right. So cool. My record was beaten. Also in 23, there was this effort, also a RISC-V emulator, this time on a Commodore 64, which means this is running on a MOS 6510, so 6502 with more pins. So this is also lower end. This was done by a guy named Ono Kortman, so also very cool. And like I said, also 2023. So I got 11 years out of this record, which is pretty cool. But I couldn't really let this happen, so I had to do something about it. But what exactly? So on one hand, it was really cool to see people trying to beat the record. That's nice. I like that. But obviously, I couldn't just let them have it. So where to? So from 6502, where do you go that's lower? I guess 8080, the grandpa of the original 8088, which started PC Revolution, would be a good start. It's much slower than the 6502, so it's an option. But 8080 is actually an upgraded version of 8008, which is an even earlier design, and it is definitely lower end. This thing takes 4 cycles to do nothing. Literally, the no-op takes 4 cycles. If you want to do something useful, it takes more cycles, at least 11. So definitely lower end. But this is 1972, so at this point, we're approaching the beginnings of microprocessors as a category. For approaching them, let's go all the way. Intel 4004 is considered to be the first microprocessor you could commercially buy. There's actually a lot of argument about whether it is or isn't the first, or whether it is or isn't a microprocessor. The definition was never chiseled into any tablet, and people do argue about this all the time. But for my purposes, it was definitely lower end than any 8-bit CPU. And this thing is kind of interesting to design with. This is before we got sort of standardized behaviors out of CPUs that we expect now. So there's some weird things going on there. It's a 4-bit CPU. It's got a 12-bit address bus and a 3-level hardware stack. So all I knew about it when I started is that it exists. I figured I've done assembly on all sorts of weird things. I've survived 8051s, so I figured I could do whatever it is. But as I started looking into it to figure out what I got myself into, I started getting a little worried, because this thing is seriously messed up to modern eyes. So this is it, 16 pins. At the time, Intel had a really big hard-on for getting things into 16 pins. That was their thing, because packaging was expensive and they didn't want to have more pins. They put a lot of work into fitting, and a lot of penalties for performance come from this. So I'll tell you some of the things that are weird about this. So most instructions are 1 byte long, but some are 2. Most instructions take 8 cycles, but some take 16. This thing runs at 740 kilohertz. They actually wanted to ship it at megahertz, which was like a big deal at the time, but it didn't work. So they shipped at 740. It has 16 registers, 1 accumulator, and 1 carry flag. The number of registers is interesting. It's actually a lot for an early CPU. So that immediately draws your attention. The reason that they put so many registers in there is that a minimal 4004 system doesn't have any external RAM at all. You just work with your registers and that's it. That was a design they considered, and there are some things out there actually using that. It's got a 3-level hardware stack. So if you call 4 levels deep into a function, tough luck. You're not getting out of there. There's 1 input pin, no output pins. There's absolutely no interrupt support whatsoever. The bus is a nibble wide, so whatever you're transferring in or out is going to be 4 bits at a time. Actually, it's going to be 4 bits per 8 cycles, so not exactly very fast. It supports 4, or if you put some work into it, 8 banks of RAM, each of which has a little over 128 bytes of RAM. At the time, nobody put together a system that big. It was very, very expensive. And you have 1 ROM bank of 4 kilobytes. Now, one thing somebody might notice if you ever played with these chips, this chip has very few transistors, 2,300 transistors. And I just told you it's got 16 nibble-sized registers, an accumulator, and a stack. That's a whole lot of state. That is actually more than 112 bits of storage there. At the standard SRAM at 6 transistors a bit, we've just blown through a quarter of our transistor budget just on the registers. Obviously, that wouldn't work. So Intel did something really sickening here. The registers, the stack, and everything are actually DRAM. They are constantly being refreshed. And that allows them to use fewer transistors for that, which is kind of weird. So if you want to use more than 4 banks of RAM, you need one of these decoders, which decode the address or the RAM select bits into more bits. This is what Intel recommends you do. It's a very strange way to do it, but that's what they do. It gets weirder yet. So the supply voltage for this thing is minus 15 volts. There's ground and minus 15. That's just how it works. So basically getting anything not designed for this to work with it is not fun. Most level shifters don't even handle 15 volts. It also needs a very strange 2-phase clock. It's active low, and the 2 phases must not overlap. To actually connect ROM to this, to run code from, you need a special chip from Intel called 4001. And to have that manufactured, it was a mask ROM that Intel made for you. You send them an actual paper tape of what you want on it, and they would make one for you. They don't make them anymore. I called and asked. So kind of difficult to even get one of these to run anything. There's also no such thing as addressing modes in this chip. There's not even a concept of addressing modes. So if you want to access memory, you will calculate the address manually. You will execute an instruction to tell the processor that this is the memory address I want to use. And then you can execute read or write instructions. If you want the next address, you're going to increment it yourself and do it again. There are no logical operations. No AND, no OR, no XOR. Yeah, that doesn't exist here. Addition and subtraction are also not quite the way you expect them now. They're always with carry. So if you just want to add 2 numbers, you have to clear the carry bit first. Otherwise, you might end up with a result that's 1 too many. And if that wasn't weird enough, subtraction instruction uses the carry bit in a very weird way. So some processors, like x86, the carry bit for subtraction means borrow. On the way in, it means the previous subtraction borrowed. On the way out, it means this subtraction borrowed. So you can chain them for longer. In ARM, the carry bit has the opposite meaning. It means not borrow. 404 guys couldn't decide. On the way in, carry means borrow. On the way out of the instruction, it means not borrow. So if you want to chain a few subtractions together, like if you want to subtract more than 4 bits, you have to actually flip the carry bit between each subtraction. So I remember seeing somewhere in an old news group that there was a plan to have an XOR gate to fix this, and somehow there wasn't space for it in the final design. But when I tried to find this posting later, I couldn't find it, so it is possible that I hallucinated this, so please don't hold me to that. All right, it gets weirder still. The code is not position independent, because that would require an adder, and that's more transistors they didn't have. So all jumps are absolute jumps. Conditional jumps are also range limited to 8 bits. But if it's not relative, what does that really mean? It means you're jumping within whatever the current code page is. So basically from 0 to 256 bytes, 256 to 512, and so on. So basically, depending on where your code is, that affects what locations you can reach with your jump. And if you start writing some code higher up above your current code, you might break the current code because you might have broken the range of your jumps. So that was all sorts of fun when I was writing code for this thing. Next up, there is an increment instruction, but there is not a decrement instruction. Sorry. There is a load to load a value from a register to the accumulator, but there is not a store. Can't do that. There is an exchange for that. So it'll exchange the accumulator with the register value. So if you actually want to store, you actually have to exchange and then a load if you want the value still after you've stored it. The input pit I mentioned, you can't actually read it. All you can do is jump based on its state. You can jump if it's grounded and not jump if it's not. The memory addressing, besides the fact that it's manual, it's also really, really weird. And I'll talk about that in a little bit. And for extra credit, the memory operations are actually not executed by CPU at all. The way it works is the CPU expects other things to sit on the bus, note during the instruction fetch that a memory operation happened, and during a particular bus phase, either put or get the proper nibble from the bus at the right time. And the CPU will just ingest it or put it there. So that means that your memory must understand how this bus works, which is the case. So the memory. So this was designed for a calculator. So Intel designed this chip for a Japanese company called Busicom for a calculator they were making. So Intel designed the memory to match. So inside the memory for this processor, there is a division of nibbles. 16 nibbles is called a register. Nothing to do with the processor register. The idea was each one of these would store a floating point number that your calculator is working on. In addition to each such register, there are 4 more status nibbles attached to it. They were designed for metadata, like to indicate that it's invalid or something like that. 4 such registers make up an Intel 4002, which is the memory chip that is the RAM for this system. This is 320 bits, state of the art in 1971. They were not cheap, I'm told. And then 4 of these make up a RAM bank. But how do you tell each one of these which chip of the bank it is? Because they're all sitting on the same exact wires. So the way you tell them is each one of these chips has one input pin that tells it whether it's an even or an odd numbered chip. And also, there's 2 models of 4002s, 4021 and 4022. So ones make up the first half of the bank, 2s make up the second half of the bank. Obviously, internally on the die, it's just an extra pin. But once again, Intel liked their 16-pin packages. So that's how this is. This is one bank. This is 256 nibbles of data, plus an additional set of those extra yellow status nibbles. That's what they're called. I'll explain them later. They're actually kind of weird. So like I said, there is no output pins on the processor. There's one input pin. All the RAMs, so all of these things actually have an output port, a 4-bit output port. Output only. You can't change the direction, nothing. So how do you do input? Well, those ROM chips I mentioned, the 4001s that Intel could make for you, they could do input or output. The reason being is runtime configuration for I/O is hard. So this thing, you told Intel how you want to configure each pin. As part of your paper tape, this was the thing you filled out. For each one of these switches, you said closed or open. So you could have inputs or outputs, pulled up or pulled down, inverted or not. You could even have pulled up and pulled down at the same time. Intel said you shouldn't do it, but they would do it for you. This means that if you're making a 4004 project today and you want inputs, you have to look for a ROM chip that's not ROM number 0, because which ROM on the bus you are is also programmed into the chip. And you have to get lucky that it has input pins. Obviously not very fun. Luckily, there is a way around this. All right. So I promised to talk about memory addressing specially. So how does memory addressing on this thing work? So first of all, like I said, you can have more than one memory bank. So you have to select the memory bank you will be talking to. There's an instruction for that called DCL. I honestly don't remember what it's called, and I don't have it in my notes. I think it's like data control latch or something. But basically, you put the RAM bank you want in your accumulator, and you execute DCL. And that makes the CPU remember which RAM bank you're talking about. If you don't do that ever, RAM bank 0 is selected. There's no way to read back the current bank. So basically, if you want to address some value and you're not sure what the current bank is, you have to do this. There go 8 cycles for you. 8 more if you want to actually put the immediate into the accumulator. Next, you have to calculate the address you actually want. Like I said, every bank has 256 nibbles. And this is a nibble CPU. So basically, we need 8 bits to address which nibble we're talking about. 8 bits is 2 registers. So you have to do the math, probably with some additions with carry, because you're only doing math on 4 bits at a time, to calculate your address in 2 registers, consecutive with an even number first. Then you execute an instruction called SRC, which basically tells the CPU, this is the memory address I will be talking to. It'll put it on the bus next time when you execute a memory read or write. RDM instruction will read a nibble from the bus, by which I mean it'll wait for some other thing on the bus to realize that RDM instruction flew by and put the value on the bus, and CPU will ingest it. So your RAMs will actually watch the bus, watch the instructions, decode them, understand you're trying to do a read, and provide the value. They will also know if they're the ones being spoken to based on what the bus phase previously told them which address was. WRM writes to the bus. There are a couple of creature comforts in this chip. There are not many, but there are a couple. ADM and SBM allow you to read a value from bus and immediately do math on it. You can add it to the accumulator or subtract it from the accumulator. This actually makes things a lot more efficient and is kind of unexpected. There's no such thing as auto increment or anything like that. So if you want to address more than one nibble of memory, you're going to go and increment that value, add with carry to the next value, execute the SRC again, and there you go. There go like 64 cycles before you've addressed the next nibble of memory. Implementing memcopy on this thing is an exercise in crying yourself to sleep. But there is one bright side. If you remember, I mentioned those status nibbles. There's special instructions to address them. In fact, one instruction per status nibbles. There is WR0 through WR3 and RD0 through RD3. And they're attached to a whole set of 16 nibbles. So what that means is you only care about the top nibble of the address to select the proper register to access its status nibbles. What that means is things you store there are much faster to access. And I actually use this to great advantage. Now, like I said, to execute code, we need a ROM. Intel is not going to make 4001s for us. I honestly called them and checked. They don't do that anymore. So how do you attach a ROM to 4004? This bus is incompatible with basically everything. It's a custom thing Intel designed, 4 bits wide, with an extra clock and an extra 1 signal. It's a total of 7 pins. And it's also at minus 15 volts. I figured an FPGA might be able to do it, but I don't know any FPGAs that can handle 15 volts. Maybe something really, really far back in history can, but that wouldn't also be very fair, because the whole point was to use an actual 404, and FPGA would be much more powerful. Luckily, Intel does have something to help, because even back then, people wanted to do something other than use Intel ROMs. They have a combination of chips, 4008 and 4009. Together, these sit on the bus, watch the bus like you have to. 4008 will watch the bus for ROM accesses, including code accesses, and wait for the 3 nibbles of address and output them on 12 actual pins that you can connect to an actual EEPROM. And 4009 will ingest 8 bits from your EEPROM and spoon feed it 4 bits at a time back to the bus. This is all nice and great as long as your EEPROM talks at 15 volts. Most of them don't. So luckily for us, there's a slightly later chip, 4289, which combines these two and has a built-in level shifter to talk to normal 5-volt EEPROMs. So these are actually pretty easily available on eBay, and they let you do this with modern things you can actually buy. It also supports input and output pins, so it's actually really, really convenient for building a system with 4004. Looks like this. So it supports a 4K ROM, which is the biggest thing you can address, and it has 4 pins that could be input or output. But you have to do some work to actually use them. When you do an input, it'll output on some pins which of the 16 virtual ports you want to access, and you have to decode that, if you care about that. All right, so what does a minimal 404 system actually look like? You will need a CPU, obviously. You will need a clock generator to generate those weird clocks. Intel does provide an alternative based on like 5 latches and a bunch of other analog components. It's not fun. You will need the ROM controller unless you can time travel and get Intel to make you 4001. You will need an EEPROM to actually shove your code into. And you will need 0 or more RAMs, depending on how much RAM you actually want to use. The Intel name for the system is MCS04. Here's mine. This was the first actual system I built with Intel 404. You'll see here there is a clock generator in the top right, the actual processor in the middle right, 1 RAM in the bottom right. There's the 4289 ROM controller in the middle, and on the left is an AppMega. It is my ROM emulator. Turns out taking a ROM chip out, sticking in an ultraviolet eraser, waiting 15 minutes, flashing it again, makes for a terribly slow cycle. So that AppMega was emulating a ROM, just for early tests. Obviously, I couldn't use it for the final system, but it was good to start with. But also, you will see some probes connected to it. It was actually about at this time that I realized that the Saleh Logic Pro analyzer actually handles these voltage levels without breaking. So I realized I had the chance to do the funniest thing ever. So I wrote an MCS004 bus analyzer for Saleh Logic. It actually handles everything. It'll understand all the bus phases. It'll decode instructions, data accesses, everything. And to make sure that if anybody else builds a system with 404 is left with no debugging tools, I asked them if they would include it in the official distribution, and they did. So the last version of Saleh Logic now includes a fully functional 404 bus analyzer. So when you decide to build a single board computer based on 404, you will not be left without debugging tools. All right, but my goal was to run Linux. So obviously it's too big and it will not fit. So how big is too big? Well, for me, Linux means I can run VI, GCC, and make, and probably enable swap to do bigger things. So that means I need 8 megabytes of RAM. I need an MMU, because UC Linux is not real Linux. You can fight me about this after this talk. Several hundred megabytes of disk space for a real Debian rootfs, because BusyBox is not real enough for me, and a serial port console. After a careful look at this, we realized that 404 can provide precisely none of that. It can't do any of these things. In fact, even if I wrote a C compiler for it, the 3-level call depth is just not enough to boot up anything. So obviously, I was going to have to emulate something. So what do we emulate? x86 instruction decoding makes me want to die. So obviously, that's not going to happen. RISC-V, a lot of people do RISC-V emulation, but the immediates are scattered all over the instruction, and that's kind of a pain in the ass as well. I was trying to go fast on a very slow CPU, so pointless work wasn't going to help me. ARM, like I did the first time, has a barrel shifter, which means every instruction can arbitrarily shift a value. As you can imagine, this CPU is not going to be great at shifting 32-bit values by arbitrary amounts. So that was kind of a no-go. PowerPC is also very complex. So MIPS wins. In fact, MIPS 1 is trivially simple to decode and emulate. Anyone who wants to emulate something, I advise you to start with MIPS 1. You can write a MIPS 1 emulator in 1 weekend, even if you're not trying very hard. And Linux doesn't boot on a CPU, it boots on a machine. So which machine? The simplest MIPS 1 machine is actually the DECstation 2100. It was a workstation at the time. It's exceptionally well documented. The documentation's available. It's documented well enough that you could emulate it in that same weekend that you used to write your MIPS 1 CPU emulator. And it's actually supported by Linux kernel right now and by Debian. You can download a rootfs that will just work, which is really kind of cool. Also, MIPS has no hardware page table walker. So even though it has an MMU, you don't have to emulate hardware page table walking, which is really nice. The software has to do more work, but you're already emulating the CPU. So the more work you can push off into the emulator, the easier it is. All right, so preparation for running Linux. Obviously, these chips are very, very expensive. They were made in 1971, and they stopped making them in the early 80s. So to prepare and to verify that my idea was actually possible, the best way is to actually not use these chips at all. So how do we solve this? Well, it turns out more emulation. But before we get even into that, how much hardware do we actually need? MIPS has 31 registers, 32 bits each. So that's 128 bytes of state. That's a whole RAM bank already. It has a 64-entry TLB, with each entry being at least 8 bytes. But it'll actually work with less. 16 entries is enough to boot Linux. And it'll scale across however many you give it. So that's another bank. I'll also need an SD card driver and a bunch of other state. So I figured one more bank for that. So 3 RAM banks. That's borderline affordable on a hobby budget. So I decided to emulate my system, which will then run another emulator, and all the peripherals it'll need. So I did that. This was my first time writing a Curses program. Really, really cool. Very recommended. Much easier than you would think. And this emulates the actual final board that I designed. And this made it much easier to debug, because this runs much faster than a real 404. I probably would not have survived debugging this if every boot attempt took me more than a week. Luckily on this, even though there is a real-time counter here, that's how long it would take on a real 404. On my system, it takes less time, obviously. On my MacBook, it runs about 1,000 times faster. This also, because this emulator is emulating 404, which then emulates MIPS, I could do cool things like pierce one veil of emulation and look into the emulated MIPS state to help me debug things, which I did. I wrote a number of checkers that checked for valid MIPS state, because it turns out emulating a hash table or writing a hash table in 404 assembly is kind of hard, considering this was my second time writing 404 assembly, first one being the Blink LED program I showed you on the other board. Yeah, I just kind of ramp up architectures like that. First Blink, second emulator for MIPS. So I started writing my emulator. By the time I had a working emulator for the MIPS CPU that actually worked, out of my 4K of flash that I had 400 bytes left. That's a little tough. I coded everything to optimize for size, including where it would cost me performance. So for example, many things that could have been unrolled as loops, I did not unroll. Logic operations, I didn't use lookup tables. I actually did them 1 bit at a time. Try to think for yourself for a second. How would you implement logical XOR if all you have is addition? It's kind of interesting. Usually you do the opposite problem, implement an adder using XOR. Not used to the other way. Turns out 1 bit at a time. Take 1 bit, clear the carry, and add the 2 bits together. The lower bit is the answer to your XOR. It's the opposite of implementing an adder. Anyways, lots of loops. But even then, I only had 400 bytes left. And what did I still have to fit in? Emulating the serial port of the DEC station. Emulating the real-time clock of the DEC station. SPI bus for my actual RAM. SPI bus for my serial port. And SD card support. I'm pretty good, but I'm not going to fit all that into 400 bytes. I still tried. I wrote what I think is the world's smallest SD card driver. 190 bytes to correctly initialize an SD card and give me a function to read and write it correctly up to spec, SDHC and not. That was still not going to help me, though, because the rest of this stuff is pretty big. So I realized I'm not going to fit into 4K. What's next? Well, ROMs have address pins. I can just get an 8K ROM and wire the top address bit to one of my output pins and do page flipping. So first, it felt like cheating. But then I found a number of contemporary devices that did the same thing. And I figured if they could do this in '71 and consider it acceptable, I could do it today. This gave me 8K of flash now. And that's really cool. Because all those things that I did in really shitty performance loops could now be lookup tables. So now I have a nibble-sized lookup table for AND, OR, and XOR. And a multiplication lookup table even, which takes in 2 nibbles and gives me a byte. That sped things up quite a bit, actually. It went from unbearably slow to mostly unbearably slow. And like I said, my emulator showed me what the boot time was, so I could actually measure how much the performance improved. But it was time to actually get to real hardware. So the goal was to make this stuff as period correct as I could. So I tried to make it very period correct. So a board has no vias, all through hole parts, and only right angle traces. It looks very cool. It almost worked. There's a couple of things here that don't exist in through-hole. The SPI RAM doesn't exist in through-hole, and the serial port chip I used also doesn't exist in through-hole. There was one that did, but it doesn't have flow control. And flow control is kind of necessary when the fastest you can accept data is 1 byte per 15 minutes. So I compromised. There are 2 surface mount chips on this board. Everything else is through-hole. What else? Well, obviously, we need some blinking lights. We need some LEDs. So this board has 33 LEDs. Also, as you see here, there's one standing here right now, slowly booting. It started last night. There's also a VFD here, a 40 by 2 VFD, because I have one lying around since a long time ago, waiting for its day, and I couldn't imagine a more glorious use for it than showing Linux output very slowly. All right, so I designed this board and had it made. On the bottom is a card edge USB-C connector, so I can power it using USB-C. I use the older Intel logo because I like it. And there's 3 banks of RAM here. I actually don't need the whole 3 banks. In the middle bank, I only need 3 of the 4 chips. But I put the footprint there for the last RAM in case someone wants to make this and use it as an actual SBC. You will get 4 actual full RAM banks. There's also a power supply here that provides all the power we need. That part was its own excitement. So like I said, 404 needs minus 15 volts. USB provides plus 5. If you want to interface with the EEPROM, you actually need something more complicated. You'll need a minus 10 and plus 5. Because the ROM control chip needs a ground pin, so it knows something to reference for its level shifters. So, and I need 3.3 volts as well for the SD card and for the VFD. Well, so like I said, I'm not an electrical engineer. I just pretend to be one. So this board having 3 power supplies is more than any other board I ever designed. So this was fun. The other thing is, nowadays switch mode power supplies are a solved problem. You can get a chip, the manufacturer will tell you the proper layout, and it'll just work. Problem is, they all assume surface mount chips, not through-hole chips. No one makes through-hole switch mode power supplies anymore. Only the old chips do it. The old ones were very, very finicky. They also use lower frequencies requiring very large inductors. You can literally see this from the back row, probably, that inductor right there. Also, they're hard to design. Switch mode power supplies are in general touchy, and like I said, I'm not an EE. First time I designed a power supply for this board, version 1, it worked kind of. It made a very annoying high-pitched whine, and it only worked when I inputted 3 RAM chips. More than that, the voltage started drooping. I talked to some people who actually do this stuff, and they told me I'm insane. But then they told me that there's some things I could do, like using a different inductor. When I asked how I know which one is correct, the answer was you just know. Okay, so I started trying different inductors. I switched to a different switch mode chip that allowed me to have an external FET. Eventually, I got a setup that worked, but made an even louder annoying whine. And then I took the inductor that I bought and started randomly removing turns of wire from it. And for some reason, that worked. Later, I found one that had fewer turns of wire. So as you see, now it's not making a loud whine. And my success, that thing can actually supply 1 amp at minus 10 volts from an input of plus 5. So that's pretty cool. The rest of it was pretty easy. So the other thing is there's signals that need to be level shifted as well. And minus 15 is a very strange level. Nothing supports this. So I expected to do some level shifting work. I honestly did not expect as much pain as I encountered. So my initial hope was I have signals that are basically referenced to my ground are either plus 10 or minus 5. I can use a voltage divider to convert that to plus 3.3 or 0. It's a linear equation, 2 unknowns, the ratio of the voltage divider and the other side. I could generate the other side with yet another voltage divider, but with very low values, and it should just work. I did the math. The ratio turns out to be 1 to 5, and the voltage on the other side should be 2.8 volts. Easy enough. That didn't work. So it didn't work in a very strange way. When the chip output a positive voltage, everything worked. When it output a negative voltage, it didn't. And I couldn't figure out why. I started measuring things. I started trying things. So you can see here the experimentation I did with randomly adding and removing resistors. This is the actual board here. You can actually look at this. Here, you can pass this around. There's nothing sensitive on this one. So that's the experiment that finally worked. So what turned out to be the issue? Well, so Intel had this really funny footnote in one of the data sheets that I didn't understand. And if I can give you one lesson to design things, read the footnotes first. Read them 5 times over. If you don't understand them, find someone who does, because always, all the shit that's going to fuck you up is going to be in the footnotes. So this footnote said, this part can be made low-power TTL compatible by placing a 12 kilo ohm pull-down resistor to minus 15 on each pin. And I read that and scratched my head. How is pull-down to minus 15 making anything TTL compatible? TTL doesn't do minus 15 anything. So I scratched my head for a while. Then I went to read the data sheet again. And I found this thing that I previously ignored. So it turns out that the transistors at the time were not even remotely symmetric. When this chip wants to output a 0, it can output it into basically a 1.2 kilo ohm resistor, meaning it can output something like 2 milliamps. But it wants to output a negative. You can see it's only guaranteed that at 50 microamps. If you try to draw any more than that, it starts getting pulled towards ground. So that's what they meant. The idea is if you add a pull down to each output pin, the pull down will help it pull down to the actual negative 10 volts that it should be giving you. And it will only give you if you're drawing 50 microamps. So that was what they meant. Now I know. But OK. So the idea is I wasn't going to do a resistor divider from a pull down thing into another resistor divider. Too much mess. So I decided to do something even scarier. I decided I was going to do the pull down they needed, put a high value resistor from there, and just use diodes to clamp it to my desired voltage level. Any ease here, please turn to your side, away from your neighbors, and puke, and then we'll resume. There are no fast signals here, no fast edges to care about, so it just works. But there'll be a lot of diodes on my board, so I thought that there is actually a thing that has a bunch of diodes to voltage and ground called TVS. So there's a TVS here that clamps everything. Yeah, this is wrong in every imaginable way. There's absolutely nothing about this that's right, other than that it works. I had to level shift a couple signals the other way to the 5-volt input levels, but shifting from 3.3 to 5 is a solved problem. Nothing interesting there. But all right, back to running Linux very slowly. I knew that everything was going to be slow. Since I had my emulator of this board, I knew that it was going to be multiple days to boot. But there were a couple of things I wasn't sure about. Obviously, I emulated an SD card. I emulated my PS RAM, and it worked virtually. But in reality, SD cards have a spec. And the spec says you shall initialize it with a clock between 100 and 400 kilohertz. I was bit-banging a clock on a processor from 1971. So the best I could actually do was 7.4 kilohertz. So 14 times too slow for the spec. So I tested this, and it turns out I couldn't find a single SD card that didn't like this. So that was fine. Next thing was the PS RAM. So PS RAM is PSRAM. It refreshes its own memory internally, so it has a limit to how long it can be selected on the SPI bus to give it time to refresh. The data sheet said 8 milliseconds. So I spent a lot of time optimizing my code, unrolling it, all sorts of stuff to fit inside the 8 milliseconds. Eventually, I got it down to average of 7.5 milliseconds selected, worst case 7.9. Then I reread the data sheet and realized it said microseconds. Yeah, at 7.4 kilohertz, I'm not doing anything in microsecond, or even in 8 microseconds. But if you think about what the purpose of this time is, the idea is this chip needs time to refresh. So we're selecting it very rarely because we're also very slow. So maybe it'll just work. I didn't want to experiment on a very slow system, so I connected it to a PiPico and purposefully started running it very slowly, and it worked. So I guess you can blow the timings by 1,000-fold and it'll still work, at least at room temperature. All right, so this is the final board that you can see literally right here. And yeah, so it works. Because of all the prep work I did in the emulator, once I got the level shifting working, this thing booted correctly the first time. You don't have to believe me, but it worked. The video I filmed that I posted on the project website was filmed the first time. I already did all the optimizations in the emulator of the emulator to know how long it would take. So it turned out that that all paid off. So if you're doing some sort of work that you can emulate, absolutely do this. This lesson I got from working at Apple, where all chips are emulated long before they ever get put into silicon. Very, very, very helpful. That emulator paid for itself in months of my time, and probably otherwise I've been too frustrated to try. Just imagine finding a bug occasionally in your TLB code if it'll take 8 hours to actually see it after the thing takes 4 days to boot. Yeah, not fun. So these LEDs on the bottom. So the emulator machine runs at about 74 kilohertz. Sorry, I'm just kidding, 74 hertz. So the LEDs literally show the current PC, the actual emulated MIPS instruction address. So you can watch it with the disassembly of your kernel to see what it's currently doing. When and if it gets to user space, you can tell where it's executing user space, which is kind of cool. But it turns out doing the output port writes is so slow that doing this every emulated cycle was slowing things down. So I do it every 32 emulated cycles. So basically about twice a second, this thing will update its PC. So you can literally see it's doing something. Yeah, it's doing something. Sorry, these LEDs are very directional, so from my angle, I can't even see them. But oh well. So that actually shows the current PC. You can watch it. The light next to the SD card is a combination SD activity and power light. Because this thing can access the SD card only very slowly, the light is on when it's not being accessed and goes off every time you read a sector. Reading a sector takes about a second. And that's as fast as I can do it. So that's basically the setup that worked. Now, you'll see that a lot of these chips on this board are actually ceramic. These are the original ones. They're the hardest to get and obscenely expensive. But OK, like I said, let's talk about how expensive this is if you want to try to do this at home. I actually went and put together this table for every component that you need to put together, and the cheapest variant of it you can get. So at the time, Intel had these dual sourced by National Semiconductor. So almost all these chips are available either from Intel or National Semiconductor. They all come in ceramic and plastic variants. And these are the prices you can expect to pay. The prices you see there for the 404 is very definitely the plastic ones. The ceramic ones are very much more because they're collectors who buy them. Some just to say they have one, which is stupid. Some to grind them down and collect gold out of them, which is even stupider. I wanted to make this project somewhat reproducible to people who want to save money. So you can actually save some money by not buying all the RAM chips. So like I said, the MIPS CPU and Linux on it will boot with fewer TLB entries. So my code will actually detect how many RAM chips you populated in the third bank and adjust to emulate a TLB with that many entries. So you can save some money on that. It'll also detect what size PS RAM you populated and auto-detect that as well and tell that to Linux. So you can save some money on that. But the modern chips are cheap, so no reason to do that. Like I said, the ceramic ones are a little more expensive. This is actually a typical price you can expect to pay if you want a ceramic 404. All the other support chips, much cheaper, which is why I have the complete set of ceramic components except the 404. And if you think the second source National Semiconductor ones will be cheaper, you're right, by about $5. This is, once again, a typical price. Sometimes you'll be able to get a cheaper one, but not very often. Now, if you want a cheaper source of an Intel 404, I will give you one secret, because I no longer need this secret. There's a very old aviation radio that is no longer used by anyone, but occasionally shows up on eBay. The model number is KX485A. That radio can usually be bought for less than $100. It contains a 404, a 4201, and a 4002-2. That is your cheapest way to get a complete set. Now, like I said, you can use fewer TLB entries, but it'll cost you performance. So, of course, I do at least something scientific here. So here's a graph. But of course, I can also mess with people. The vertical axis doesn't start at 0. But this is actually how many MIP cycles it'll take to boot to a command prompt in Linux across how many TLB entries you have. Obviously, you need a minimum of 2, because you have to be able to fetch your instruction and at least 1 item of data. And as you see, after about 4, the payoff is pretty low, so you can save on the chips. All right, so before I take questions, if anyone's still awake, I have an FAQ, because there's a couple questions I keep getting. First one is, how long will it take this thing to actually compile and run Hello World in GCC? I got this one enough that I tried this. So this is an actual picture of when I started it. Here's a picture of the output 1 month and 16 days later. But it works. You can see here on the left my serial console with the source code and the output. Next I get is, can I try this without building hardware? I mean, yes, you can use my emulator of the whole system, but that isn't really a faithful emulator in many ways. Luckily for you, there are other people as messed up as me out there. So a guy named Vas Crab, who is a developer from MAME, when he saw my project, thought that he could do a funny thing. So he went and emulated my board in MAME. It is officially supported in MAME right now. You can download the binaries from my website, give it to MAME, and it will emulate this board and actually boot Linux. Yes, because MAME actually has realistic emulation speed. So the screenshot he gave me here is much faster, but it will work in real time because MAME does that. And the next question I get is, what's next? So I obviously hope that people will continue trying to beat this record because I think it's hilarious. But if they don't, my plan is to do a new project about every 10 years, since that's about the cadence I've been on right now. I've already picked the next one definitively, which will be a 1-bit industrial controller, the Motorola MC14500B. And the next two after that, I'm still thinking about, but most likely one will be a board of only transistors, and one will be a board of only vacuum tubes. So that is my hope, at least. We'll see if I live that long. But I'll probably get the 1-bit industrial controller thing done. But I do encourage people to try to actually beat this record, because it is kind of fun. And also, you can never justify it to anyone. It's only for fun. There's no purpose for this at all. Absolutely nobody needs to boot Linux in 7 days. So there's actually a full write-up covering a lot more than I could say here. I tried to cut it down to 1 hour. I tried reading it very quickly myself, and it's about 8-hour read. So this is the QR code you can scan, or you can just go to the website and find it. It's one of the top things here. A couple other things. If anybody actually wants to do this, I have a couple of PCBs for the latest revision. So if you're, or at least you think you're going to do this, there's 3 boards here. You can just come and grab one. If anybody actually wants to attempt to replicate this, you can just come and grab one of the boards. Save yourself that effort. The other one is, while debugging this, I found that my output from Linux was off a little bit. Some of the characters were a little bit off, literally in the console output. It's still booted, though. So after a week of debugging, I found that one of my RAM chips had a weak bit. And when you'd store a 1, it would sometimes read back as a 0. It was one of the RAM chips storing the actual register state of the emulated MIPS CPU. Yet somehow Linux booted, despite the fact that one of the registers would occasionally lose a bit. Booted all the way to user space. But it happened that that bit was affecting a memcopy inside the kernel. So yes, memcopy was also broken. It's still booted. And I then wrote and designed a Intel 402 memory tester. But this is the chip that has 1 broken bit. So if anybody wants it, the first person to yell out that they want it can have this as a souvenir, if anybody does. Anybody want a 402? All right, I saw that hand go up there. Sorry, you were second. And if anybody else has other questions, I am happy to attempt to answer them. Yeah, go ahead. So after the optimization that I put into it, it takes 4.7 days to get to the command prompt. And then each command takes a while. For example, ls takes about 20 days uptime. 20 hours. Uptime takes about 16 hours. And I wrote a Mandelbrot set generator in integer only. That one runs in about, I think, 16 hours as well. I have a video on my website. Actually, I guess we have time, so I can actually put the video here. Go ahead. DRAM, yes. Yes, exactly. It's just perverse to store your registers in DRAM. It is just not a thing you would ever expect to do. So I'll skip past the boot to the part where something interesting actually happens. None. So luckily power didn't go out anytime. But here you can actually see the clock down there in the background. That's the Windows clock. And you can see the minute hand swiping across there. This is sped up a lot for uname running. I'll find the Mandelbrot set. It's here somewhere. There it is. So you can see the actual time when that started. It was still typing. So it checks for interrupts about once every 15 minutes. So you can at most input one character every 15 minutes. So there you go. So it started at 7 p.m. and there you go. It's generating the Mandelbrot set. I'll just leave it running in the background. If there's any more questions, I'll take them in the meantime. I think that was the first one. That's the second one. Luckily for you, I used the USB power cable down there that shows it. 6.3 watts approximately continuously. So actually not terrible. And there was one more question here. It'll work. This is full Linux, full Debian. I don't think you'll have to write the entirety of Doom using no more than 3-level call stack, which might be a little tough. But once again, I have, luckily for you, designed a working 4004 SBC you can now make, complete with all the Gerbers and everything else you need on your, so you can actually try it. If you want to do it on the emulated MIPS, it will absolutely work. No. No. I will just emulate MIPS. MIPS turns out to be one of the simplest machines to emulate. MIPS 1 instruction set is very, very amenable to emulation. All the immediates are in one place. The decoding is very easy. If you want to emulate something, especially in a constrained system, it is much easier than anything else. So the question is, which normal processor feature did I miss because of all the oddities? Honestly, I missed the store instruction. Just ability to store some value somewhere. Because you're stuck thinking, can I survive with exchange or not? Almost all the exchange instructions end up followed by a load back of the same value. Because usually you want to store something and then do something else with it. The other thing I missed, logical operations. You don't know how much you value AND until you don't have AND. I mean, emulating is one thing, but all my code had to be written without AND altogether. It's a little weird to write code without logical operations. So I published, the assembly for 404 is pretty easy to read. There's only like 25 instructions. So you can look at the code that I published and see it's easy to read, but if you start trying to write code for the CPU, you will notice that you're missing a lot of things that you take for granted. Any other questions? All right, cool. Thanks for coming. If anybody wants a board, come grab one.